Can you create a Venn diagram that sums up mass, weight, and change in motion? Let's see. If we had two circles, everybody's familiar with a Venn diagram, right? Maybe this one is the acceleration due to gravity, or G. This one is mass, whose variable is lowercase m. And maybe right in the middle here, where you have both mass and an acceleration due to gravity, you're going to have that force known as the weight. Does that make sense? In order to have weight, you have to have both a mass, an amount of matter, and a gravitational field, as Newton might say, or a curvature in space-time, as Einstein might say. We're mostly going to go with Newton's definition, though. Mass is an intrinsic property that measures the quantity of matter in an object. Your mass does not change if you go into space. Weight is an extrinsic property. Intrinsic means it's peculiar to you, and it will not change in various locations or circumstances. Weight, however, is extrinsic in that it depends on something on the outside too. So mass only depends on the amount of matter you have. Weight, on the other hand, depends on the amount of matter you represent interacting with a gravitational field. So these are forces that act outside of you as a result, and these are an inherent property of the amount of matter that you have. So your weight changes if you go into space. Your weight depends on your location. Mass is a scalar quantity. Scalar only has an amount. So scalar is amount only. So 60 kilograms is an amount of matter. There is no direction associated with a scalar quantity. Weight is a vector. It has a magnitude and a direction. It's always acting in a particular direction. For objects on Earth, it always points straight down towards the center of the Earth. That's why the people in the southern hemisphere and in Australia, they don't fall off, because for them too, the force of their weight acts to the center of the Earth. Forces are vectors, and we typically represent them with arrows. The size of the arrow's length, is proportional to the size of the force, and of course the arrow's direction points in the direction of the force. So this is actually a very convenient symbol for forces. In fact, it's a very convenient symbol for any vector quantity, any quantity that has direction. For example, forces. Weight is a force of gravity acting on objects with mass. Weight is mass multiplied by the strength of gravity, or the acceleration due to gravity. It's actually sort of a special case of the second law, where the net force is equal to mass times acceleration. Here, the acceleration is the acceleration due to gravity, the mass is the mass, and the net force is the weight. At the Earth's surface, the strength of gravity is 9.8 newtons per kilogram. And let me just restate this a little bit. Since a newton is a kilogram meter per second squared, and we're dividing that by, actually we're not, let me just rewrite that a second. So a newton is a kilogram meter per second squared, as we said a couple of slides back. And we've divided that by kilograms. The real units for acceleration are meters per second squared. Sometimes you might see it written, oops, I'm going off the page, as a meter per second, which is actually the same thing, because if I'm dividing two fractions, I just keep change flip and they're all the same thing. So don't be fooled by newtons per kilogram. It really is just meters per second squared. 1 kilogram of mass weighs 9.8 newtons. This is roughly the mass and weight of a 1 liter bottle of water. And here's the calculation. If you like, you could use 10. That's fine with me. You'll get 10 newtons instead of 9.8. Pretty close, I say, unless you're looking for fairly high precision. Force is a vector, so it has a direction. The force of weight always points straight down, again, towards the center of the Earth. What changes if you bring this bottle to the moon? Well, that's an interesting question. What changes is the acceleration due to gravity on the moon, because the moon has gravity. It has no air, but it does have gravity, although it's less. It's roughly 1/6 of the Earth's gravity, or something like 1.6 meters per second squared, or 1.6 newtons per kilogram. Okay. So there we go. 1 kilogram times 1.62 newtons per kilogram is 1.6 newtons, which is roughly 1/6 of the original weight. Well, what's a pound? The pound is the English unit of force. The person standing on this scale is pushing down on it with a force of 125 pounds. Okay, that's fairly self-evident. 1 pound is 4.448 newtons. The newton is a smaller unit of force than the pound. 1 newton is 0.225 pounds. A little less than a quarter pound.